Okay, I will continue with the examples. First, noiseless binary channel. Okay. So I'll use these pictorial diagrams to represent the physical channel or the statistical channel. So here is the input, here is the output of the channel. And when input alphabet is equal to 0, this picture shows that the output is 0. That is basically the probability of x equal to, y is equal to 0 given x is equal to 0 is 1 because there is no other output. And this one says when y is equal to 1, x is equal to 1 is equal to 1. Okay, and there is no other possibilities. When x is equal to 0, output should be equal to 0 with a probability 1. That's what it means. When the input is equal to 1, output is equal to 1 with a probability 1. Okay, so that's noiseless binary channel. It talks about input alphabet, output alphabet, and the channel, which is P, Y given X. What is the capacity of this channel? Basically, the capacity of this channel, we can talk about, basically that is, that can be written as h of y minus h of y given x. And what can we tell about h of y given x? Given the input, output has no uncertainty. So this one is 0. So this mutual information can be written as, in this particular channel case, as entropy on y. Y is, as you can see, is a binary random variable. So it is less than or equal to 1.0. How do you make this binary random variable as the how do you make this binary random variable so that the entropy of y is equal to 1.0? So that is the case when y is equal to equally likely random variable. Okay, so that can be achieved, equality can be achieved when y is equally likely. Then how do you, this is about maximization over input distribution, not the output distribution. So how do you make the output y equally distributed? By controlling the distribution of input x. That is the case when input distribution is equally likely, right? Equally distributed, equiprobable, right? So when you use half and half, then probability of y given 0, that is basically equal to probability of y given 0, y is equal to 0, and x is equal to 1. Probability of y given 0, x is equal to 0. You can talk about it, but this probability is 0. That is the what's left. Then basically probably x is equal to 0, and the p y given 0 given x is equal to 0. This is equal to 1, so this is p of x is 0. Okay. So you can change this to 1, but using the same procedure, this is the same. Okay, so p of y given y is equal to 1 is equal to p of y, x is equal to 1. So the input distribution and the output distribution is the same. Then this equality can be achieved when px equiprobable distribution, then equality is achieved. Equality is achieved when px is equally probable distribution. So since it is achievable, the capacity is equal to 1.0. So C in this case is 1.0. We have to use bits per channel use, and so on. All right. So that's the explanation for capacity of noiseless binary channel. Okay. Right. Let's go to the other example. So noisy channel with non-overlapping output. So in this particular case, what is going to be the capacity C? So again, we have to talk about maximization over px, mutual information between input and output, and so in this case, this is the alphabet of x, alphabet of y, given like this. So you have now 4 possible element. Four possible outcomes of the channel. And here, the probability distribution for x is equal to 0. So this is y equal to 0, x equal to 0. That is half. This one is p, y is equal to 2, given x is equal to 0, like that. And this one here is p, y is equal to 3, given x is equal to 1. And this one is p, y is equal to 1, given x is equal to 1. So that's the conditional distribution, and that's the channel that you are given with. And then the question is, what is the capacity? So in this particular case, you can invoke our previous results. Basically, you can see that there is no overlapping of outputs. So in this particular case, you can talk about mutual information. That is equal to entropy of y minus entropy of y given x again. So when you choose x is equal to 0, entropy of y, you can talk about, so 0 you can talk about, right? And entropy of y given x is equal to 1. You can talk about this way. And you notice that since there are 2 outputs, you can see that this could be up to 1, right? Each one of them, right? And the other case that you can talk about is you can utilize different derivation for mutual information. So instead of using this, we can talk about mutual information. Entropy of x minus entropy of y given, x given y, right? Now we can talk about this one and then given the output, right? So for example, y is equal to 0. entropy on x, y is equal to 1, entropy y is equal to 2 and 3 and so on, right? What can you tell about this? So basically for this one, so y is equal to 0. So at this point, do you have uncertainty on x? No, you have zero uncertainty. How about y is equal to 1? Same. It should be, the input should be 1. So there is zero uncertainty. So the measure is all 0. So this part is 0. That means it is only about maximizing the input distribution so that the entropy, maximizing the entropy of the input, finding the input distribution that maximizes the entropy of the input, which is equally likely again. So in this particular case, the mutual information is upper bounded by 1.0 log 2 of 2, right? And the equality is achieved with input distribution px, which is equally likely. So half and half. So if you use these two symbols, equally likely, then equally probable, then the capacity is achieved. Capacity C, the maximum is achieved, and the maximum value is 1.0. So C here is 1.0. It can be achieved with equal equiprobable distribution. Okay, so that's the result here. All right, let's move on to noisy typewriter. So the noisy typewriter is drawn this way. So basically, there are alphabet from letters from A to Z. There are 26 of them. So that's the input. And the output is 26 characters again. But this typewriter is noisy. When you try to push the button A in the typewriter, it actually types A or B with equal probability, right? Half and half. So that's the case, and we just talk about it. So this is the probability I have, and the same with the rest. So basically, is a half of y is equal to b, x is equal to a is half. That's the conditional probability. So that's the channel. In this particular case, what is the capacity? Okay, so now we can see that these symbols overlap with each other. Okay, in this particular case, what is the capacity? And the capacity again is maximum mutual information, where maximum is taken over the input distribution. And using the definition of mutual information, we can write this as this, entropy of y. So again, input is here, y is the output, and the entropy of y given x. Okay, so when x is given, the output A and B are equiprobable. So the entropy of y given x is 1, because it is the same for every other inputs, right? So that this part is determined, that is 1, because the channel is given, okay? And then we can talk about the entropy of the output, entropy of the output. And then entropy of the output is upper bounded by log 2 over 26, right? So that is the case when output y is equiprobable over the 26 letters, okay? Then the question is, how do you make the output y equiprobable? All 26 occurs equiprobably. That is the case when you make x equiprobable. Okay, so that's how you achieve the capacity. So that is log 2 over 26, right? For entropy of y, and since this one is log 2 of 2, then using this minus sign here, move that into the ratio, right? 26 over 2. Then the capacity is log 2 over 13. Okay. All right. So that's the capacity, log 2 over 13. That's the capacity of the noisy typewriter. This can also be achieved by using different input distribution. Let's say use every other symbol only. Let's say use A, use C. So do not use B, do not use D, and so on and so on, right? Use Y, but don't use Z. Then you are only using 13 symbols. When you're only using these 13 symbols, you can get rid of the overlappings. And in such a case, you obtain log 2 of 13 as well. So there are multiple solutions to achieve the maximum mutual information. But the capacity, the answer doesn't change with the different px. So in this particular case, the px is 1 over 13, 0 over 13, 1 over 13, 0, and so on and so on, okay? So that's the noisy typewriter problem. This problem is very important. This picture is very important because that will tell you the big picture view of channel capacity theorem. As we increase the number of symbols, this picture will appear again with the law of large numbers. So you basically, when you choose an input symbol, and P of X give you a distribution of output, as long as you don't have this distribution of output do not overlap with each other, then the probability of error can be controlled and you can achieve, you can define the capacity of this case. Then basically capacity is the number of code words that you can choose at the input space of vector, a set of vectors. In this particular example, 4 vectors. Basically, that's the capacity of this channel. As long as you don't have them overlap, and you can control the probability of error very small, then you can satisfy the statement that capacity is the set of code words, size of the message set as you increase n such that almost no error, you can transmit the information. So in this particular case, since there are 4, basically the size of the message set is 4, and then log 2 of 4 is 2 bits. So you can send 2 bits of messages using n channel uses that is the length of this typical set. Size of the, I mean, the length of each code word. Okay, we'll talk about this more, right?